last time we started to talk about the nanofiltration. And we have been mentioning that in nanofiltration, for the first time, we are also introducing materials where the selectivity can be related not only to size, dimension of the particles and dimension of the pore, but also to the fact that the membrane material can be charged. We can have some polyelectrolytes, that means some molecules in which fixed charge are present in the structure of your material, and this fixed charge can be positive or can be negative. And we define it in this system ions that we call counter ions, which are ions having a charge opposite to the charge of the fixed one in the matrix, and co-ions, ions having a charge which is similar to the one of the fixed charge. The difference between these two systems is that the counter ion can penetrate, can enter in the polymeric phase, in the membranes in this case, and for each one entering, one will move out in such a way that electron neutrality is always respected. The same cannot happen when a co-ion is entering because the fixed ions cannot move out. So if something is trying to enter, we are going to we violate the electron neutrality and something is going to happen. What is happening is that we create a donor potential, a difference in electrostatic potential that will exclude, will move out ions having the same charge of the fixed ions in the matrix. This kind of phenomenon is very well present in nature and is called Donnan exclusion. The potential we create are called Donnan potential, and they can have an influence on the selectivity of nanofiltration membranes. Basically, this is a mechanism for which monovalent can be separate from bivalent, because the effect is related to the charge of the ions, and so we can separate easily in nanofiltration monovalent by bivalent. The transport of electrical charge in our system is given by, if you have electrical charge moving across the membrane, we have just electrical flux across our system, which is just given by the product of the charge of the ions, of the single ions, to the mobility of the ions, and to the concentration multiplied for Avogadro numbers and the unit of electrical charge. And this is the overall, for the different ions which are present, that will be the electrical flux in the system. F is just Faraday, the number of mole equal to the Faraday number. Basically, we can express our current in the system using this Ohm's law just by considering the flux of all the ions that are going across, multiplying for the difference in the electrostatic potential across the system and for the membrane surface. So that will be the expression of, that is the difference, the distance between the thickness of the membranes, or the difference between the electrodes that are present in the system. Now, what is the Donnan potential? If we have a solution containing ions, charged components, and the membrane that is separate these two solutions, assuming that at least one of the ions can be permeable in our system, that is going to go across, if we want to have equilibrium in the system at the interface between the membranes and the ions, the electrochemical potential of the species has to be equal in the membrane phase and in the solution. And that is the expression of the electrochemical potential in the system. When we have also an electrical field, a difference in the electrostatic potential, the chemical potential is becoming electrochemical potential. That is the chemical potential we already defined, plus the electrostatic field. And that is what is called electrochemical potential. Basically, the electrochemical potential of single ions has two terms, the chemical potential and the electrical potential multiplied for the gain Faraday constant and the valence of the single ions. What we call Donman potential is nothing more than different between the electrostatic potential of the single ions in the membrane phase and the electrostatic potential of the ions in the solution. So that's what we call this Donman potential, and that is the potential that has been created if you just want to separate the ions in the system, just to respect the electron neutrality. This is the kind of expression that we have to consider. Here we are just writing our system in terms of the difference of the pressure in the membrane phase and in the solution. We can just introduce, as we made already, instead of the partial pressure, this osmotic pressure. And so we can just rewrite the Donman potential in terms, instead of the activity, we just use, instead of the pressure, we can introduce the osmotic pressure. You can elaborate the system considering the condition of the equilibrium. And if you do this, respecting the electron neutrality, this kind of equation is coming true. But that's what you have to remember more than this, is the most important equation, which is this one. In general, the Donman potential, by the way, is between, assuming that we are in an ideal system, that means a solution relatively low concentration. In the first approximation, assuming introducing concentration instead of activity, the difference between the electrostatic potential, membrane phase, and solution is given by the RT for the log of the ratio of the concentration of the ions in the solution and in the membranes. And that is the kind of equation that you have to consider. Now, if you just go through the system and you try to establish the condition of equilibrium between the ions in the membrane phase and the solution, at the end, introducing the condition of electron neutrality, this is the equation that is coming through. And that is the important one, because this equation is explaining what is happening in our system. This is the concentration in the membrane phase of the co-ions. So the one having the same charge of the fixed ions. This is the concentration of the fixed ions in the matrix, in the membranes. And this is the concentration of the ions in the solution. And what is happening, they are coming with the square. What does it mean here? That if the concentration of the fixed ions is big enough, is significantly high, this concentration will be significantly low. That means no co-ions can penetrate. Take in mind, this equation has been, if you make also the analysis, is coming through for respecting the electron neutrality. That means high concentration here, low concentration of co-ions. But if this concentration is becoming similar to the concentration of the co-ion, that means if this concentration is becoming very high, or this concentration in membranes is very low, the exclusion does not work anymore. And that is important because it means that when you have ion exchange membranes and you want to utilize the system to exclude some ions, you must be always sure that the concentration, what we call, this concentration is also called charge density. The charge density of your membranes. That means the number of fixed ions of a certain charge for grams of membrane, for square centimeter, how do you want to define. But if this number is very high, this number can be very low. So the membranes is acting, having a good exclusion. But if this number is becoming very low, or if this number is becoming very high, at one point the system does not work anymore. Today, when we will discuss about the blue energy, and you are discussing about electrodialysis, reverse electrodialysis, and we want to have a high power density of the order of 20 watts per square meters. The problem is that for having this very high value of power density, we have to work with very high salinity for your solution. Seawater is not good enough. Instead of seawater, we are working on a brine. For example, seawater is 0.5 molar, 0.5 mol per liter, brine can be 2 molar, 3 molar, 5 molar. So if you, in this case, in principle, you have very high density, power density. But for having a membrane active in terms of high selectivity at this high value, you need a very high charge density. Otherwise, there's no exclusions. The system will not work as a selective membrane, so you cannot create a reverse electrodialysis. So you have to produce today new membranes at very high charge density. And that is an interesting area, as I was mentioning already. So remember, this kind of equation is interesting because that is the conclusion for all this analysis in terms of Donan potential, telling that when this ratio is high, that means when there is a high charge density compared to the co-ions, the system works nicely. That means, and this concentration has to be always a concentration relatively low compared to this fixed charge that we have here. So this one, if this one is increasing too much, this compared to fixed membrane don't work anymore. All this discussion is telling us at the end that basically the partition coefficient, we have to introduce a partition coefficient because this number here, we don't know how to measure. So as we discussed already last time, we have to introduce a partition coefficient, and the partition coefficient in this case is given by 2 contributions. One contribution is just related to the selectivity, as in ultrafiltration, related to the size effect. Bigger particle will not penetrate in the pore, etc. But there is also another term related to the Donan effect, to the charge effect, which means that the overall transmembrane flux in nanofiltration, as you can see here, is more complicated than the one that we have been discussing before in ultrafiltration, also assuming eventually that both terms have an influence, the pressure and the chemical potential. In this case, there is another term, which is this one, because there will be always a difference in concentration between the two phases of our membranes. So this term exists, and we also have to consider the effect, the electrostatic phenomena related to the fixed charge present in the system. So nanofiltration is the most complicated of the pressure-driven separation process, because in nanofiltration, if you want really to understand and to predict eventually the selectivity in terms of the flux of the single ion across your membrane, you have to consider the effect in terms of the hydrostatic force and in terms of difference in pressure across the membrane, in different chemical potential, but also in terms of the electrostatic field which exists in the system. We will see that in reverse osmosis, for example, this term does not exist. So basically, reverse osmosis is much easier in understanding and in predicting than nanofiltration. It's very difficult today to find in literature people working in trying to understand transport mechanism in reverse osmosis membrane. Basically, if you click on the web, you don't find too much. If you click on the web in nanofiltration separation, you still find people trying to develop a theoretical model to understand and to predict basically how you can realize good membranes to have good separation. And there's a lot of discussion which is the best model, because all these terms are present and they are a little bit complicated to analyze and to predict. So that's an area, and that is related to this the charge effect, basically. If you want now to understand what is happening in nanofiltration in terms of the selectivity of your membranes as function of the effective hydrostatic driving force, delta P minus delta pi, or in terms of the increasing concentration or increasing the driving force, you can see that the selectivity for the different flux, now because increasing the effective driving force, the solvent flux will increase, and also the solid flux will increase, much smaller increasing, but both increase, and that will be the behavior of the selectivity of your membranes as function of the effective pressure on the system. In terms of concentration, if you are increasing the concentration, the selectivity has just different effect. Increasing the concentration what you are doing, you are reducing the driving force because you are increasing delta P, and that means delta pi minus delta P is becoming lower. So just the effect negative compared to this one. So what is happening when you are increasing concentration is that the solvent flux is decreasing just because you are decreasing driving force. The solid flux opposite is just still increasing, and that is the behavior, the overlapping of these two plots. Assuming that here is a constant hydrostatic pressure, and here was a constant feed concentration, obviously, you have this kind of behavior. That means the overall fluxes are just decreasing, increasing the concentration. If you go again now in real life, and you are looking for commercial membranes, as we saw in ultrafiltration until now, you can find a lot of commercial membranes on the market. And what is interesting today, there are new field, new area, new company entering the field, producing membranes. All these ones that I'm showing here are just for aqueous solution. An interesting area of research today is the field in which the solvent is not water. All around the world, there are petrochemical company, there is pharmaceutical company working in nanofiltration membranes for non-aqueous solution. And that's quite interesting, and also in this department, there are somebody looking to new material that can be utilized in this way. If you want to recognize nanofiltration, except for the symbols, you will see that, for example, salt rejection here is no more very high, because normally in this kind of system, first of all, the applied pressure that you are necessary is much lower than the one we will use in reverse osmosis, but higher than the one you normally use in ultrafiltration. Ultrafiltration is normally 1 or 2, 3 atmosphere. Here you can have 5, 6, sometimes you can have 7, 10. But the selectivity is relatively low. Years ago, when I was a student, if producing this kind of membrane were bad membranes. You are put in the garbage. They don't work. No high selectivity. They are not useful. Today it's just the opposite. You go in the garbage, take out again, and just you can develop new application just using membrane with relatively low selectivity. So don't be nervous if you don't have 99%, etc., because there are some specific application where we need this kind of selectivity for salts, monovalent, sodium chloride, etc. But when you have for sodium chloride this selectivity, if you now look the selectivity for sugars, for some amino acid, some dyes, or drugs, some different kind of drugs, antibiotic, etc., this can be just 40%, maybe lower. In some case, can be just 3% or 10%, but amino acids 90%. So you can clean, you can separate some contaminants from your final product using this kind of system. Most part of the pharmaceutical today are going in the very final stage through nanofiltration, where you remove all the salts and you just concentrate the active components, which are normally much higher molecular weight than the sodium chloride and similar. So in principle, it's in quite interesting area. You can see in some cases also here, they are instead of talking about the rejection, they talk about the cutoff I was mentioning in ultrafiltration. This is not interesting, very scientific definition, but remember, cutoff means that 90% of the components having molecular weight higher than this 400 in this case don't go across the membranes. So that's the definition. 90% does not go across. In this case, you can have a cutoff of the order of 400. Remember, sodium chloride is 58 as Dalton. This is 400 Dalton. That means that can be an amino acid or a lot of pharmaceutical. Sodium chloride, potassium chloride, lithium chloride, salts are going across, so you can remove easily, and you can concentrate the components of interest. That can be 1,000 Dalton, 400, 200, etc. You see here that you have a wide spectrum. You can separate salts from species having 600, 800, 200, 400, 1,000. So that can be quite interesting possibility to separate chemicals of interest having a wide spectrum of molecular weight using membranes of this kind. And these species are the one which normally added value, the real product that at the end you want to have. So that you can recognize, and you can see a big company, General Electric and Nadir, Nitodenko, Koch Engineering, Hydronautics, these are all big groups, they all produce nanofiltration membrane. 15 years ago, these membranes were not existing. And 15 years from now, in this area, there will be new membranes. Not very much in ultrafiltration, not very much in reverse osmosis, but in this area, yes. And particularly for species working not in water, but in organic solvents, stable in organic solvents. If you have any polymer that you know is stable in some organic solvents and not yet utilized as membranes, check, because that can be a field of interest. In fact, we are looking to these things. There will be in Europe, next 5 years, a lot of projects on new membranes for nanofiltration application. Evonik, for example, I mentioned already, which is one of the largest chemical groups in Europe, today just went in the Imperial College, one of the big universities in UK, where there are some professors producing some nanofiltration membranes stable in organic solvent, and they just bought all the team, create a company with Imperial College only for producing nanofiltration membranes. And that's happened a couple of years ago. Okay? Again, here you can see a large variety of this material, and each one of these is basically this number here is giving the cutoff, the selectivity of your membrane. So it's a wide spectrum of a system that you can utilize. Most of them are normally in spiral wound, flat sheet, in a spiral wound configuration, or in some case also in hollow fibers. Dow is another company producing these elements. Here I'm talking about the elements because you will never see the membranes. What you have in your hands normally is a module block. You don't see nothing inside with an entrance and exit, and inside there are your membranes. And General Electric, again, you see, has a lot of this material. Now, the most important of the process, of the pressure-driven process we have been discussing, is reverse osmosis. And reverse osmosis is the most important because reverse osmosis is a process already applied in large scale, in huge plant. Some of the largest plants for desalination today are no more thermal system, MSF, etc., but as we discussed in our introduction, are just 100% based on membrane system. People are not familiar with this, the people have no idea, but you can have a huge, incredible plant, I mentioned single plant, installing 3 million square meters of membranes in a single plant. Huge system, and producing more than 70%, 75% this year of the water produced worldwide is already related to membrane system as reverse osmosis, which we are considered today what we call dominant technology. There is no competition. If there is any other motivation to compete, it's nothing to do with the technologies, tradition, local motivation, fact that, for example, in Saudi Arabia, energy in the past was not a problem, so they were using burning oil because oil was available. But today, the situation is changing. Just to remember, you remember that osmotic phenomena are phenomena in which if you have a semi-permeable membrane where only water can go across, and if you have just fresh water on one side and the seawater on the other side, what is happening normally is that the only way to have equal chemical potential for the water on both sides of your membranes, that means same concentration basically, is to just move water from the dilute side in the more concentrate, trying to dilute also the seawater. If you do this, what is happening that you will see that you are increasing here the hydrostatic, the level of the water column, that you are creating hydrostatic pressure, and at one point you arrive at quasi steady state, and the difference between the level here and here is just given tell you the osmotic pressure of the solution, which is related to the concentration through the Van 't Hoff equation. If you want now not, by the way, this is the way to create energy, because if you increase and increase and increase, and after this water fall down, and you put a turbine down here, you just are transferring the Gibbs-free energy from chemical energy in mechanical energy and in electricity if you have a turbine. And that is a part of the blue energy we will discuss later. And, but initially, the problem for us, nature is producing energy in this way. We were not looking to energy, we were looking to water years ago. There was water stress. So somebody said, if this is true, let's try to move in the other direction. So if you apply here an hydrostatic pressure and you push the water across the membranes, no salt can go across because the membrane is always semi-permeable, ideal semi-permeable, so only water can go across. And if you apply the pressure higher than the osmotic pressure difference, you have to overcome these limits. The water will not penetrate, but will move out. So we produce fresh water. And that's what is happening today. And so the system that we have, in this case, is again, if you want to understand what is happening, here there's still discussion, the effect eventually of porosity, also in these membranes. But to make life easier, we don't need to talk at all about porosity here. We have to talk about a new mechanism we call solubility diffusivity model. So in this case, nothing to do with microfiltration, with ultrafiltration, where the mechanism was just convection, viscous flow across the pore of your membranes. Nothing to do here with charge effect, as in nanofiltration, but just solubility and diffusivity. What you have to assume that in this case you can have some of the chemicals present in the solution, seawater, water and the sodium chloride. The water can be easily dissolved in the polymeric system forming your membranes, and when after this dissolving on one phase of your membrane, it will diffuse across because you are creating a concentration gradient across these membranes. So you just have first step solubility, second step diffusivity. The product of the solubility coefficient and the diffusion coefficient is what we call permeability in this case. And that can be one of the mechanisms. Some other people are trying to describe and to predict again the selectivity of these membranes, assuming that pore also in this kind of membranes. But if you want to talk about pore here, this pore has to have, you can see the pore. If you go to the positron annihilation instrument, pulse, and you want to see, for example, understand selectivity for boro, which is a big problem, some people are discussing the quality of the membranes on the basis of some pore in which boro can pass or cannot pass. However, when you are at this level, the size of the pore combined with the electric constant is giving you this difference in selectivity, has to be of the order of 2-3 Armstrong, which is not, we don't call pore when there are 2-3 Armstrong. This is the size, if you have, for example, any molecules, any polymer, but no, DNA is an helix. Internal to the helix, there is a pore, and this pore is about 2 Armstrong, 2.5. But we don't call the DNA a porous material. DNA is just, this is the configuration of these macromolecules. So we call dense material in this case. And that's why we just discussed about solubility and diffusivity. If you want to assume a pore, you can calculate the potential energy of water in a material having a certain dielectric constant, and with water having a certain dielectric constant, and you can calculate for the water and for the ions. And if you do this calculation, Rautenbach was a guy that, Gluckau years ago made this calculation, you can find that the ions prefer to stay outside and not inside. And that can be origin of the selectivity. But it's much more complicated to predict. And this model is relatively simple, and 95% of the experimental results that we have today can be well explained using this kind of mechanism. So if this is the mechanism, some assumption has to be introduced. For example, that flux are independent. This is not the case, but no kinetic coupling between different fluxes, solvent and ions. Total volume flux is first approximation equal to the flux to the solvent. The solid flux due to the pressure gradient is negligible, is small compared to the solid flux due to the activity gradient, concentration difference. That's why we are talking about diffusivity. And so these assumptions are present in the solubility diffusivity model. And if you, assuming this assumption, you can write the flux of your ions across the system exactly as we have been discussing in nanofiltration. And that you can have just the term with the difference in the activity, and that is the way in which we can just elaborate our system. There will be one term that is just the different in the pressure, and one term that's different in the activity. Remember that when we discuss about this system, the concentration here is the concentration at the membrane surface. So that's in the membrane phase. This M means concentration of the ions in the membrane. So we don't know it. So also in this case, we need to introduce a partition coefficient telling us this value, how to calculate this value depending from the concentration in the bulk and the partition coefficient. So you need to know for each material which is the partition coefficient for the single ions, and this is a thermodynamic number, so it depends from the temperature. So in principle, you need at each temperature the appropriate partition coefficient. If you do this and introducing this approximation that we have been assuming, so that means that the flux, the volumetric flux is the water flux, and this product is equal 1. For the solute, that we can express in terms of the difference in the differential of the activity, and osmotic pressure can be introduced using the Van 't Hoff equation. And if we just make the integration in along the cross-section or the thickness of your membrane, and in terms of activity, the activity you can express in terms of osmotic pressure, at the end, what you can obtain with the basis of the assumption is the total volumetric flux, and the solid flux given by the volumetric flux is given by the effective pressure that we learned already, delta P minus delta pi multiplied for the diffusivity, RT, and this molar volume in the membrane system. And the solid flux is the same term in the term of the concentration of our species and the diffusion coefficient in the membrane phase. So these two expressions are giving you the total volumetric flux and the solid flux. Introducing this partition coefficient, concentration of the ions in the membrane phase and in the solution, you will just have the final expression, which is nothing more than volumetric flux proportional to the driving force, as we mentioned already in the very early stage, through a coefficient that is we call a permeability, which is nothing more than the partition coefficient for depending from the temperature, diffusivity, and the partial volume. For the solute, same story. The solute flux will be proportional through the partition coefficient diffusivity to the different concentration between the feed side and the permeate side. So these are relatively simple equations. However, they are totally wrong. These equations that are written this way don't trust too much or try to understand exactly, because these equations tell you that the volumetric flux, the overall flux across your membranes, or the salt flux, is related, the volumetric flux depends from delta P minus delta pi. But remember, delta pi is a function of the concentration. And this linear function with the concentration. If the concentration in the solution is increasing, delta pi is increasing. And that means the driving force is decreasing. Now, when you have your membranes and the membranes start to work, what is happening is that water, in a good membrane with high level of selectivity, water is going across the membranes. But salts don't go across the membranes. And what happened to the salts? The salts accumulate on the membrane surface. That means we are increasing the concentration just on the membrane surface. And so this equation has to be corrected because this term here is continuously changing. Why is we have this increase of the concentration? Because convective flux across the membranes, is creating the accumulation of the salt that don't go through. Now, the salt, how can be redistributed in the solution? Only by back diffusion. Back diffusivity is very slow compared to the convection flux. So you accumulate salts. So you have to find a way to minimize this phenomenon. This phenomenon is called concentration polarization phenomena. It's this one. So if you don't keep control of what happened at the interface, forget about the bulk. Because in the bulk, eventually in the big volume, nothing happened. The seawater does not change the concentration during your process of desalination. But at the membrane interface, the concentration is changing continuously and very fast. Because you have all the solution, the convection across the membranes, and that means water only is going through, and all the salts are not going through. So these salts can also only be back diffused in principle if you don't do something. That means the driving force for the salts accumulated here is just given by different concentration through diffusivity. Much, much smaller than the convection that you have here. So initially your solution, before starting to operate here, was a uniform concentration in any points in the bulk system. Now, as soon as you start to operate, you are creating concentration profile in the solution. That means increasing the concentration at the interface, and this is the concentration that we wrote in the equation. It's not the bulk concentration, it's the CM, which is controlling the system. So we have to keep control. If CM is equal CB, no problem. The equation we wrote before is valid. But in few tenths of a second, from the moment you start to operate, the concentration here is CM, is no more CB. And that is the concentration profile. So if you don't keep control of the concentration profile, the system does not work. And if you make all the analysis, and you can make eventually, or I will pass you can see, will realize that in a few seconds, depending from the pressure you apply, the concentration that will go across the membranes, you know which value will have. Here you have a nice selectivity because entering with seawater, 0.5 molar, and here you are going out with 200 ppm, very, very diluted. But if you don't, when you do right, when this concentration is equal to this one, with your selectivity of 99%, rejection 99%, if you don't do anything and you operate in this way, in a tenth of a second, what is going through is exactly CB. The concentration on the permeate side will have exactly the same value of the bulk solution. And when you're looking this one, you say, okay, change the membrane, you make no, something is broken. We just broke down the membrane. Not at all. The membranes was perfectly working, but it's not working against CB. It's working against CM. And CM was no more 0.5 molar, was now maybe 3 molar. And if you make again the calculation, you'll see that the concentration they have downstream exactly appropriate. So you can apparently, you have a broken membranes, but it's a question of fluid dynamics. It's a question of how to destroy this concentration profile. Okay? That's why all this, we can just make calculation on this, and having what I was mentioning, that is the film theory that is giving you the possibility to predict exactly what is going on in the system. Just to consider that no membrane system, normally what we call membrane separation system, is working in a dead flow. That is the case I was mentioning before. All the operation we have been discussing are operations in which the bulk solution is running at high velocity on the membrane surface. And the motivation is just so you spend energy, but just to destroy, to facilitate this back diffusion. You are creating mechanical mixing in the system in such a way that it's not just back diffusion, fixed law, controlling the removal of the salts, but is a significant turbulence that you can create. And I was mentioning here, you can work with velocity that is 5 meters per second, very, very fast, with Reynolds number that can be 20,000, 25,000. Otherwise, the system does not work. Also in this case, which is this most interesting, you have a lot of membranes on the market. These are, as you see here, big names that are just, and new names are coming in, by the way. China, Korea, and other countries are now producing their own membranes and more. And when you go to see some of the characteristics of this membrane, you will see here that the salt rejection is no more, as we saw before, 40%, 20%, 30%. Here, there will be never a cutoff. Cutoff here does not mean anything. You will only talk about salt rejection, 99.9, 98.5, 99, 99, 99, etc. So very high value. Pressure, normally that you can obtain here, is of the order 20, 30, 40 atmosphere and more. Big value. And also in this case, however, when you just have a characterization of your membrane, you are always supposed to give in which condition. These numbers are not universal. These numbers are always much related to the fact that you have been working with solution 0.5 molar at a certain temperature, at a certain pressure, etc. So because it's not easy to transfer from one solution to the other. First approximation is possible, but depending, you can have compaction phenomena changing the pressure, for example, and you can have some the difference related to the way in which you've been making the characterization. So when you make a test, when you give some numbers, it's always useful that you know in which condition these numbers have been produced. So you will find always the condition of reference, basically. But rejection, quite high, pressure, quite high compared to the other case. Some material, you will see here, we will not discussing about how to make the membranes, but you will see here that we are talking about thin film composite membranes. And here we were talking also about thin film. This is one of the way to make asymmetric membranes. If you remember, by the way, I forgot to tell that all the membranes in reverse osmosis are asymmetric. But the way to make asymmetric membranes, as I was mentioning in the introduction, are two different ways. You can produce asymmetric membranes by phase inversion. That means having one polymeric solution, and if you know how to do it, starting from what we call a polymeric solution in a certain with solvent and non-solvent present, you can evaporate and you can make from liquid phase go to the solid phase. And this is what we call phase inversion. It's a very sophisticated technology. Today, we understand the most part of the system, and you can controlling the different parameters, concentration, temperature, kind of solvent, kind of non-solvent, quenching solution, etc., you can form an asymmetric structure. Very, very regular on large scale, and that's what is going in many systems. However, another way of doing is to use a traditional membranes as a support, and on this support to create another very thin film of another material. And this is what we call composite membrane. And thin film composite membrane, TFC. Most of the membranes utilized today industrially are of this kind of configuration. There was a guy, a student as you, that a long time back, Cadot, was just producing in the lab this kind of system. He was making a coatings, basically, by in situ polycondensation of some polyaromatic polyamide on a polysulfone or some other materials, obtaining quite interesting results. So you will find, and these are asymmetric membranes, dense skin on the surface, very dense, and porous material on the back, giving mechanical resistance and no high pressure drop in the porous part. And the results are quite interesting. One thing here just to mention, to remember, you will see some of these material, For example, this one, polypiperazinamide, complicate materials, a little bit expensive, difficult. There was a lot of interest still today in producing membranes for reverse osmosis quite resistant to chlorine attack. Now, chlorine is a very strong chemical product, which is quite very much used on large scale in the disinfection of a lot of solution, including in desalination. And so if you are going to use membranes for desalination, people were trying to have material stable to chlorine because the chlorine is the most traditional way to disinfect water, etc. Forget about this problem now, because, again, I mentioned some already in some problem reach. Today, chlorine is still utilized. When you are in your kitchen and you have to clean something or clean the floor, you are using sometimes chlorine. In perspective, the chlorine in Europe is already going to be banned. There is side effect of chlorine, not immediate, but when the chlorine go in the system, it can induce some chemical transformation in different compounds, which at the end are going to create problem to health, etc., on long term. So in Europe, chlorine is slowly disappearing. Big company has to redesign how to produce something. For example, textile company, bleaching cannot be done anymore with chlorine. It has to be done with acetic acid or some other bisulfite, etc., not chlorine anymore. Which means that some of these membranes designed only for having chlorine resistance are not so important anymore. And that's, on the other side, you can have more material, but you can see basically polyamide, aromatic polyamide are also, this one is also an aromatic polyamide, by the way, but are the ones that are more used. And all of them can be just produced in flat sheet and organized in spiral bound module. Rejection, you can see here, all the same order of magnitude. So before suggesting new membranes in RO, be sure that you have something really different than what all the other people are already trying, have been produced already. And you can find a lot of these membranes. Just to give you an idea how many they are, that means give you an idea how big is the market today. And still people are using also the first membrane, celluloacetate, still quite interesting. This is the first membrane with just celluloacetate. And Japanese people, particularly Toyobo, is also making fibers with this kind of material. And you can see how different can be for different application. High rejection, and in some cases specifically done for boro. Boro is a big problem because when boro, if you concentrate boro during desalination, after you don't know, this boro is going again in this in agriculture, etc., creating troubles. So you have to find membranes with a very high selectivity for boro and a specific membrane having this kind of properties. And we know about boro, but tomorrow will be the same for some other metal that we still don't know what is happening in 50 years or 100 years of using water with concentration different than traditional one. But the boro case is very well known, and membranes have been designed just for boro, etc. We will not discuss too much about how to make membrane, but just to give an idea that if you want to study about new membranes, polymers have been already explored. We know everything about polymers, or approaching everything, and so it's difficult to invent a new polymer that can compete with all the polyamide or the study of celluloacetate, etc., etc. So if you have something new, have a look, but be careful because a lot of stuff has already been done. Vice versa, we need better membranes in nanofiltration, in a certain sense also in reverse osmosis, but not for improving a little bit, make no sense, too much money just to produce a new membrane, but for changing significantly and to make a real breakthrough in terms, for example, chemical resistance, in terms of temperature resistance. We don't have RO membranes working at more than 70 degrees, 75 degrees at most. If you can go with some material at 120, 130 would be very nice, a lot of new application. We don't have inorganic RO membranes. I did not mention, but you can have nanofiltration inorganic. We can have ultrafiltration inorganic, ceramic, etc. No RO until now. People are trying, but very difficult to make skin, dense skin with inorganics. That's why people are still looking how to produce a dramatic transformation in reverse osmosis. And you can see here this possibility for nanocomposite material, nanotubes, and biomimetic are the three areas which has nothing to do with a different polymer, but different methodology, different transport mechanism. And basically, this possibility in some cases exists. And these are some examples, for example, of how to produce new kind of materials, new kind of membranes with some new properties. These are not just for RO, but this is, if you want to have super hydrophobic materials, you can just do with this kind of template that can form just a very regular homogeneous distribution. And the same case is here, where we have this control phase inversion in control atmosphere to have a regular pore side distribution, and it's for basically ultrafiltration, microfiltration. And the most interesting case, if you can really try to make a hybrid membrane, combining nanoparticles, fullerene, for example, in some polymeric matrix. This is one thing that people are trying to do. Now, fullerene are quite interesting materials with very interesting adsorption properties. Remember that is solubility, diffusivity. So if you can change in any way the step of absorption, that can be quite interesting because you increase the concentration of the membrane surface, and that will create a bigger driving force for the transfer of the ion in terms of diffusivity. And fullerene can be interesting because they can have specific absorption properties. If you want to try to do something in gas separation, for example, and you have some material that can block CO2 and not nitrogen, etc., that can be a way of doing. So people are trying to create some fullerene membranes just by entrapping the fullerene in the system. Not easy to produce 3 million square meters of membrane that we are doing with polyamide, but that's something that can be done, and people are looking to this. More than this is the case of carbon nanotubes, and you will find literature already, many people trying to do this, including ourselves. However, if you want to use carbon nanotubes, you know nanotubes, people have been exploring a lot of interesting properties, incredible high flux across the system and high selectivity. Still not clear why. There is still people trying to understand the origin of this very high selectivity and permeability that we can have in carbon nanotubes. If you have some good ideas, that will be one of the future Nobel Prize. The understanding and predicting. However, if you want to use this carbon nanotube, you have to produce membranes in this kind, with all the carbon nanotubes organized, very well oriented, such a way that the permeate is going inside and across. Today, most part of the people, you have a mix. You are producing a composite material, so you can change mechanical properties a little bit, impermeability, but for sure, not the 110,000 more than doing this traditional system. If you're able to produce this kind of form, that can be quite interesting. The other way of doing is, again, to learn from nature. In nature, if you go in the literature, you'll find that few of the last Nobel Prize have been given to people who have been able to understand the high selectivity of biological membranes to water. We transfer water in all our membranes, and this happened through the mechanism, the fact that we have in our biological membrane some protein, specifically aquaporine, and the aquaporine is creating a channel with a specific, as a carbon nanotube, specific high permeability and selectivity. So if you are able to separate, produce aquaporine, and immobilize aquaporine in biological system, in our artificial system, you can try to reproduce what aquaporine is doing in nature. In this case, people are trying to do this. There are people who can try to sell you aquaporine membranes. Don't buy. I will not invest a penny in this kind of thing for real application. You can take a nice picture, but I don't think it will work on large scale. However, that's an interesting idea, and if we are able to produce a large amount of aquaporine at a relatively small cost, and to realize nice membrane which simulate biological one, that can be interesting. With aquaporine or with, again, other protein. Because keep in mind, when nature is doing something as a reason, but we can do better than nature. So nature has been doing in aquaporine. Now, if we realize how aquaporine is working, we can try to produce cheaper and easier to grow protein, having similar properties, it's ferritin, etc., for example, and trying to reproduce the same. When we will discuss about membrane catalyzer, I will show you some membranes in which we are trying to immobilize protein across our polysulfone or peak, just a crystal of protein going across, trying to reproduce exactly this kind of configuration. So that's an interesting area of research where we are active and trying to do something, and it will take time, but can be just a way to make a real change in the final structure of the membrane we are producing. The most interesting today, and interesting for you because in this department there are people with experience in graphene, is to make what we call graphene membranes. Now, why is interesting graphene? Because graphene is the same as carbon nanotubes. There's one difference. Carbon nanotube is three-dimensional, and you have to make the orientation and to put all these tube in parallel, etc. Until now, not easy to be done. In principle, can be done. Electrical field or some specific orientation in some solvent does not work. At least if you're really working, you're not able to succeed easily. Graphene is bidimensional. It's not three-dimensional, so you don't have the problem of orientation. What you have to do is to form a thin film, ultra-thin film of this carbon structure on a traditional membranes. And if you can induce some permeability, graphene is impermeable in principle, very hydrophobic, but impermeable. You can make, first of all, graphene oxide, which can become hydrophilic, or you can induce some defects in your graphene. And these defects, if you're able, can be also well controlled. You can try to have defects of certain size. In nature, we are already using this concept, not for graphene, but for perovskite. I don't know if you know what is perovskite. Perovskite are some other materials, crystals, present in nature. A lot of perovskite are in Africa, for example, and people are predicting that Africa will be rich in the future when the perovskite will become more utilized. Perovskite are crystals, so no solubility diffusivity, no size effect eventually, because the crystals are barrier to mass transfer, but full of defects. So if you have a vacancy of oxygen, there are a lot of perovskites are mixture of different metal oxide normally. In the crystal, if there is a defect, for a vacancy of oxygen, you have just a possibility to have oxygen entering, jumping the vacancy. There are many vacancies, and you have oxygen jumping from one vacancy to the other one. So you have selectivity 100% only for oxygen. Trouble is that this kind of phenomenon is activated at high temperature until now, at 800, 900 degrees centigrade. So you can today extract oxygen from air and make your steam reforming of methane, producing hydrogen basically, using just perovskite membranes. Same story that we are talking here. Perovskite membranes, we have been spending millions and millions of dollars. All the petrochemical companies are involved in producing perovskite membranes for the steam reforming, for hydrogen production. But here the same, if you can control defects in the graphene, you can produce systems of different size, by the way, where some permeability, some transfer will become easy, and you can utilize all the properties of this material. Graphene or graphene oxide, and as you know, in this department, there are people producing technology for realizing this ultra-thin film of graphene or some graphene oxide in some support, and that can be quite interesting approach. These things don't exist yet at industrial level, but in perspective, they can be realized. I was mentioning before now that membranes are an important part of this story, but for what we are concerned, we will not talk too much how to make these membranes and how to use these membranes. They exist, and for the moment, we trust that they are available. But we want to see which are the other problems which characterize all the membrane operation, as I was mentioning, is the concentration polarization is issue number one in pressure driven. When we are talking in other kind of process, as membrane distillation, you will see that these concentration gradient are not so severe in creating problems in system as membrane distillation, but temperature gradient are very severe. Temperature gradient are also present in reverse osmosis, in principle, but you can easily control, and normally in reverse osmosis we don't increase temperature, so it's very difficult. You can create some situation if you have a warm solution on one side, and you can produce a lower temperature on the other side, but normally this is not the case. So we don't, and in this case also, the effect of the temperature polarization you can create is only related to the fact that diffusivity, viscosity, density, all the transport parameters of a solution are function of the temperature. In some case, increasing diffusivity or decreasing viscosity. So in principle, if you change temperature, you are changing the transport parameters which are present in the thermal proportionality between driving force and flux. So you have to take care of this. But this does not affect too much on the driving force of the system. In membrane distillation, you will see that we don't have any effect significant on concentration polarization, but dramatic effect on temperature polarization. In this case, it was just the opposite. Remember that there are two kinds of phenomena we are going to describe. One is concentration polarization, but after this, we will also have to discuss another problem, which is fouling. Fouling, and particularly biofouling. The two things are very separate. However, they are interrelated, because if you don't keep control of concentration polarization, in some case, you can induce fouling. That means concentration polarization, and we saw before, is increasing the concentration at the interface. Now, this increasing of the concentration of the solutes present in the solution at the interface can be at the origin of fouling. You can have increased concentration, so you're increasing adsorption. You can arrive to a point that increase the concentration, you approach saturation, and you have a change of phase. You're becoming, some of the solids precipitate on the membrane surface, scaling. All these problems are present. They are not the same. Concentration polarization is reversible. When you stop working, the concentration profile will disappear. Slowly, less slowly, depending from the viscosity, but will disappear. Fouling cannot disappear. In some cases can disappear, in some cases will never disappear. Part of the fouling is irreversible. You can change completely the property of your membranes. So you have to consider both cases. In some cases they are related, but in some other cases they are independent. You can have a fouling also in situations where there is no concentration polarization, just because some chemicals can interact with the polymeric matrix. I gave you an example last time, telling that if you don't change the polarity of your membrane, for example, you can foul very quickly when you have a painting with a certain charge, and if the charge of the membrane surface is opposite to the one that is present in the solution, the two charges will interact. If the same, the two charges will just reject. So you must be very careful. So we can define the formation of concentration profile upstream and also downstream. Normally we don't take care too much of downstream, but sometimes downstream can have an effect on all the transmembrane flux of the semi-permeable membranes. We can also induce cake or gel layers formation at the very end. But this is one, what we call concentration, and that is only just concentration profile. Fouling can be a consequence of adsorption, deposition of the feed, interaction, etc., and eventually we can have also concentration that will facilitate. Both cases, we have to keep control of the situation. what is the concentration polarization we already have been discussing, and here is the situation that we are talking about. Again, what you have here on your solution, you can have the concentration in the bulk at a certain level, but during the permeation of the water across, you will accumulate some of the solutes. The solute can only back diffuse in principle, and this back diffusion is much lower than the convecting here, and that means you can create this concentration profile. The way to analyze and to predict this kind of phenomena is to use basically the film theory. The film theory is telling that also when the equation that we have to consider here is just that the convective flux to the membrane surface plus the back diffusion is equal to the concentration in the permeate. This is the mass balance that you can just realize in the system. The way to control, by the way, the phenomena is what I already mentioning. We have to use basically hydrodynamics. There's nothing to do with the membrane properties, with no membrane material. You have to introduce some other way to control changing the feed flow velocity or the module design. Today there is a lot of things that can be done. You can vibrate the membrane, for example. You can induce some, you can have on the membrane surface some kind of moving molecules having the function of a local turbulence promoter. If you have, in nature it exists, if you have on the membrane surface some small molecules, a kind of protuberance on the membrane surface, these protuberance can be quite active in removing, if you have the appropriate thickness, in avoiding the formation of the concentration profile, etc., etc. And for sure, it depends also from the kind of solid and kind of concentration. Basically here, the methodology to reduce concentration polarization are different. You can just reduce, by the way, this is very important, because this is one of the points that telling you have to understand what is happening. Reduce the pressure is one of the best way of doing, or to reduce concentration in the membrane surface, or to reduce solids in the feed. These are the three basic approaches. Now, reduce pressure is the most interesting one, but is exactly the opposite that what normally people are doing if they don't understand the problem. If you have to produce 50 cubic meters per day of water, and suddenly the time of the running out is coming, and you are already being produced 40 cubic meter, what people are doing is, let me increase a little bit the pressure so more water will be produced, because they know that there is a linear relationship between flux and the driving force. So it's, and you increase a little bit the pressure, and you increase the pressure and some more water is going through for a few seconds. But if you just increase the pressure and do nothing more, after a few seconds of increasing, you have a dramatic decrease, because you are increasing concentration polarization. If you increase just the pressure and more water is going through, more salt will accumulate, and if you don't do nothing, the phenomena is bigger. You're increasing concentration on the membrane surface. Operators in the past were doing this way. People not experts for the first time, etc., when the flux was low, they were increasing the pressure, and apparently the flux was increasing. But after some time, plant was going to collapse. If you want to increase the pressure, you can increase the pressure, but you have also to increase cross-flow velocity, such a way that you mix more than before. Otherwise, there will be just negative effect. So be careful. You have to reduce the pressure. If you reduce the pressure, less salt will accumulate, and you just have less concentration polarization. So just the opposite that what people were assuming on the basis of the equation I told you wrong. Because the equation that I wrote down was, you said flux is proportional to the driving force. So if I increase driving force, I increase the pressure. But the driving force is not delta P. It's delta P minus delta pi. And so for any reason you increase delta pi, system doesn't know. But this is a little bit more sophisticated than just telling proportional to the delta P. So you have to understand what is concentration polarization. So this is one way. The other way to reduce the concentration of the membrane surface, and there are different ways of doing this. You can just mix, stirrer the solution. You can have just remove the concentration by boundary layer skimming, by mechanical scarring in some case, etc. Or you can reduce solid defeat. That means reduce concentration, basically. In nature, we are working at very low. We don't have concentration polarization phenomena in our body. We are all membranes, except when some problem exists. When you have problem, concentration polarization is taking place, by the way, in your blood or in our other system. Normally, the way in which we are working at a very low velocity and low concentration. And that's another way of doing. The way to realize this, for example, is a thin channel, short flow length, increasing diffusivity, that means temperature, and that's diffusivity, and also just diffusivity or decreasing viscosity is also related here. Or the best way of doing high velocity gradient, or moving the membrane or move the liquid. That's the other two way of doing. That's the way for which all the traditional filtration are normally working in this dead flow. And this is large scale of units still existing. But today, all the membrane systems are always characterized by very high tangential flow. I told you this can be 5 meters per second, 3 meters per second, and more than this. High turbulence promoters are always present in this situation. If you want now to try to predict and to analyze what is happening on the concentration profile, is not so easy, because all these parameters are changing with time, changing with concentration, etc. So if you make the real flow dynamic analysis, it's not easy to integrate your equation. However, there are some, you can introduce some hypotheses, and the system can be analyzed in a little bit easier way. For example, the film model is the one that is normally utilized to describe the mass transfer that you have in the situation, in assuming that with the film model, basically we have a situation in which also, if you are working in a turbulent flow at a certain distance from the membrane surface, at a certain distance from the entrance, you always have a constant laminar boundary layer, which is established adjacent to the membrane surface, and in which longitudinal mass transport is negligible low. So the mass transport within the film can be one-dimensional, perpendicular to the membrane surface. And that's what is normally done. So you have to integrate basically only across the boundary layer of the system. If this is the model that we can utilize, you can try to predict the concentration in the bulk and the concentration at the interface. So you can, you have the JS, the solute flux across the membranes, the solute flux by convection to the membrane surface, and this is the solute flux from the membrane surface back in the solution. And you have just to integrate in the thickness of your system, assuming that the concentration at the level here is exactly the same than in the bulk, and here you have the concentration at the wall. And what you are normally assuming during your integration is a linear behavior, not concentration profile, but you can assume that the linearity here, so you can have a nice expression for the concentration at the bulk, at the interface here, if you know the concentration in the bulk. This case that is relatively simple, assuming that nothing happened at the interface. The situation is a bit more complicated when, due to the concentration polarization, you can also induce some solid precipitation at the membrane surface. The kind of phenomenon that you can have is the one described here. That's typical for protein in ultrafiltration, for example, where you have a transmembrane flux and you are increasing your pressure. So from the equation that we wrote for ultrafiltration, you are expecting that increasing the pressure, you are increasing linearly the transmembrane flux. With this result is present, but only for very low increasing of the pressure. As soon as you start to increase a little bit more, what is happening is that the flux is becoming independent from the pressure. At any level of concentration, if it's just water, it's just linear, so the equation is valid. But when in the water you dissolve, for example, a protein, at different level of concentration, what is happening? At one point, it's becoming constant. And this, for a real application, is quite interesting and important, because it makes no sense to go and increasing more pressure if the transmembrane flux does not change. So you want to know at which point for each concentration you can have a deviation from linearity. So that is one of the parameters we want to understand, and that's what we call a critical transmembrane flux. This is the limit transmembrane flux. That is the highest value that we can have, is the limit. And the critical one is when we start to have this deviation from linearity. Both of them are quite important for any industrial application and development. The way you can see this same phenomena can be controlled by changing the flow dynamic condition. If you are in a situation where you have a different kind of concentration, changing the transmembrane flux, changing the steering, or that means the axial flow rate, for example, you can see here, you can change significantly the level of the critical flux, or also the level of the limit of flux, by just increasing basically the turbulence on the system. And that is related to the formation of boundary of precipitate or jellification or just absorption on the membrane surface. When you are in this kind of situation, the equation that you have to consider for your volumetric flux is this one. There is no more just, there is a proportionality between the overall transmembrane flux and the driving force across your term of proportionality that we learn what it is, but what is changing here is that the membrane itself is changing with time. The membrane itself has an intrinsic resistance that you can measure when you measure in water and just the slope of your plot, but with time you can induce some other resistance additional to the initial one, and this, for example, can be related to the formation of a certain deposit or a thickness or a gel, what it is, of a certain level, and that is the thickness of the layer that is additional to the thickness of the membranes that was characterizing the membrane resistant at the beginning. Okay, we will discuss about this kind of system next time, and there will be different equations today available. Most of them are phenomenological, that are trying to predict as much as possible the transmembrane flux as functional driving force when the system is a little bit more complicated than the one just water or water and sodium chloride. And that aspect I was mentioning has the same importance than the aspect related to the property of your membranes. The principle is membranes can also have an influence on this kind of phenomena here, but is not immediate influence, is not the one you can easily control. So that's why we have to see which kind of equation we have to utilize depending from the understanding of the property of your solution and what can happen. Scaling is a term that is familiar to you because it's present in many other situations. It's also present in membrane. Scaling means deposit, for example, of calcium sulfate, carbonate, salts which are present in the solution. But in membranes, it's much more than this. The effect of the scaling can be dramatic in blocking completely the operation, and so we have to find a way to control, assuming that our membranes are always working. As the case I was showing before, its membranes can be just seawater going across. There's no hole. It's just that the flow dynamic of the system was not very well designed. And you have to change the flow dynamic, not the membranes. Okay? Okay, we meet next week again.